So, we started looking at the practical issues that involve the construction of a laser. So, in the last class we said that there are certain requirements for making or constructing a laser. So, what are those things that we need in order to construct a laser? So, to make a laser or construct a laser, we need, most important thing is the active medium. So, your active medium is the one that can give rise to population inversion and hence laser action. So, the material that will have electronic states that can give rise to population inversion can work as an active medium. So, you can choose the particular type of material system that you want based on the the kind of laser that you want, based on the type of frequency that you want, based on the type of power that you want. So, you can choose systems which are like maybe a 3-level system or 4-level system. And when we talk about this particular material, as we mentioned, so an example of 3-level system is ruby. So, and a 4-level system is neodymium doped yttrium aluminum garnet or YUG. So, this is the most important thing to choose first, and the second is the source of light that will excite the atoms to higher excited state. From there it will laze. Okay. So, we said that this is known as pump. So, we need to have a pump, all right. So, this is nothing but some light source. Which can be a flash lamp, which can be an electric discharge system depending on your medium and requirement. So, these are the two primary things, and with this we can start constructing a laser. So, let me show you. So, first what we will do, we will take our active medium. Okay. It can be a small crystal of that particular medium, it can be gas if you are talking about gaseous laser system. So, whatever that is, so I have that active medium. Okay. So, next we pump it using some light source. Okay. So, this yellow one is my active medium and this white arrows just signify photons coming from the pump source. So, once I get these, then what will I get? I can excite the atoms within the active medium to the respective state, which can ultimately give rise to population inversion. So, I can create the population inversion. So, in the first step, so step 1 is excitation, which will lead to population inversion. Okay. These things we have already learned. I am just reiterating again and again, so that we are absolutely clear about the whole mechanism. Okay. So, once the population inversion is created, I need to create stimulated emission, right. So, second step will be stimulated emission. Now, the question is how the stimulated emission will be created. Say, for example, I am taking a 4-level eraser, okay, 4-level system. Suppose I take something like this. So, then what is my system? My system is like this. So, first excitation will take this system over here, okay, and then it will come back by non-radiative transition, and here population inversion will be created between these two states. So, atoms are here. So, up to this point I have created. Now, I have to create the stimulated emission. How it will be happening? Because my source is such that its energy corresponds to this gap. Okay? So, this arrow corresponds to the gap between the level say 4, 1. So, I have say in this way, suppose I write, okay, which may be different from the last class, but you understand this. Okay? So, this energy gap is much more than this energy gap, right. So, this delta E, say I say delta E 2 3, and this delta E is delta E 1 4. So, delta E 1 4 is much higher than delta 2 3. Now, in order to create a stimulated emission, I have to give photon of the energy delta E 2 3. Okay. So, how we can do that? We do not need to supply any light from outside. Why? Because these atoms sitting at level 3 will at some point of time relax back to here by spontaneous emission, right. So, it will have spontaneous emission. So, we are showing it by a straight arrow. Okay. So, this spontaneous emission will give me a photon which has this energy gap. Now, this photon, if it interacts with this active medium, meaning that it will interact with these atoms sitting at level 3, and it will trigger a stimulated emission. Okay. So, this spontaneous emission will create a stimulated emission. So, I will get 2 photons out of, due to this one spontaneously emitted photon. Now, those 2 stimulated photons, if they interact with the active medium again before leaving this medium totally, then they can trigger again stimulated emission. Okay. But if they leave this active medium, then of course we lose them. Then we have to again wait for another photon coming through spontaneous emission to cause another set of stimulated emission. So, although we are getting a stimulated emission, but we are not in a condition to create a laser. So, in this picture what we get? We get light out of stimulated emission of radiation, true. Okay. So, in this I get this one, but there is something missing here, right. A is missing, meaning that amplification, that is another criteria, right, that is the main criteria to get a laser output. So, the question is how do I amplify, right. So, question is how to amplify. It is clear that in this condition, this stimulated photons are not going to create a huge amount of further stimulated emission, or the only spontaneous emission is not going to trigger huge amount of stimulated emission, and thereby no amplification. In order to get the amplification, what we need is to put this system within a resonator, to be precise, within a resonator cavity. So, what is that resonator cavity that we are going to deal with? We are going to create a resonator cavity by placing two mirrors. Okay. So, we put this system in a resonator cavity, which is created out of two flat mirrors M1 and M2. What are the characteristics of these mirrors? M1 and M2 will be extremely flat. Okay. Whether we can make it or not, we will see later, but at least to start with, we do not see much problem in having a extremely flat mirror, okay, with reflectivity of 100%. That means these guys are 100% reflective. So, if the reflectivities are R1 and R2 for M1 and M2, that is 100%, that is what we say. Okay. So, we create a cavity by making this two, putting these two in parallel configuration, and then put this active medium along with the pump source in the middle. So, now what will happen? Let us see that in an elaborate way pictorially, so that it becomes very clear to you. So, now what I have after this excitation creates a population inversion, first thing is that it will start emitting photons spontaneously. Okay. So, the spontaneous emission will have its own frequency, and all the spontaneously emitted photon will have same frequency, okay, because the spontaneous emission is going to take place from this level to this level, okay, not from here to here directly, okay. That is by design. So, spontaneous emission will take place, okay, randomly. So, it can go in this direction, it can also go in the direction which is along the axis of this cavity, which means the axis which is perpendicular to the mirror planes, all right. So, this is my axis, right. So, this is my axis of the cavity. All right. So, now the spontaneous emission will go in every possible direction, because they are very random, okay. So, some of them will be going in this direction. So, what will happen now? So, these photons which are going in a direction other than the axial direction, they will not go and hit this mirror and return, rather they will escape. So, this photon will escape the cavity. It is very easy to understand, okay. So, they are not falling on the mirror. Even if they fall on the mirror, then they will again go out, right. But this photon which is moving along the axis, that will be reflected back here and then reach here, passing through the active medium. So, it will start bouncing off between these two mirrors, and every time it will go through the active medium, causing more and more stimulated emission. Makes sense? Absolutely, right. So, if I look at this problem in a stepwise manner, I am not bothered about the active medium, we know that it is there. Okay. So, I am just drawing these photons. So, there will be spontaneous emission all the time. Okay. So, this photon, okay, so this photon will now bounce back and hit here. So, what will happen when it will go here, it will create 2 photons, right. And in the meantime, there may be another spontaneous photon which is along this axis, fine. So, in the very next step, what I will see is I will see these 2 bouncing back and making 4 photons, while this one will bounce back and it will pass through active medium, create 2 more photons. So, I will see and then the spontaneous emitted photons are always there. Now, what I am seeing is with every round trip, there are more and more stimulated emission and they are increasing, right, 2 to 4, 4 to 8 and so on. So, after a certain time, what I will see is this. I will see exactly this picture. So, these are all stimulated photons, and then as usual there will be some random spontaneous photons, right. Now, coming from this one to this one, we can easily see the ratio of the number of stimulated photons to the spontaneously emitted photons are becoming higher and higher and higher. So, the number of stimulated photon, or in other words, the stimulated photon density exceeds the spontaneous photons by a huge number, okay? And that is what we want, and this is what is called amplification, right. I started with one spontaneous photon going in there, and then I am getting more and more. So, every round trip it is getting multiplied, multiplied, multiplied. That is what is called amplification. So, this is the So, in some way we can say this place we are having kind of a seeding. So, we are planting a seed and ultimately this is getting amplified. So, billions and billions and billions of photons are created within no time, right, because these cavities, if we have a practical sense, it will be a few tens of centimeter, maybe 100 centimeter or so. So, that is traversed by light. How many times? You can very easily calculate that by knowing the speed of light, right. So, you will see billions of times they are coming back and forth. Okay. So, the number of photons are also getting multiplied. So, stimulated photons are the predominant species within this one. Now, by design, stimulated emission have the same property as that of this spontaneous photon. When I say it has the same property, I mean actually the identical. So, it will have the same direction that the spontaneous photon was moving, it will have the same phase, it will have the same energy, that is same frequency, same color, okay, same polarization. So, everything is identical to this spontaneous photon, and when I amplify them, all of them have the same property. So, that is a wonderful thing, right, and that is why one needs a light source like laser instead of a conventional light source, all right. Excellent. So, so this is my resonator cavity, right. So, I can see having a resonator cavity, we can amplify the stimulated emission. Fine. So, we have got the stimulated emission amplified, but what about the output? I have chosen these mirrors to start with to have 100% reflectivity. That means no light can escape here, all right. So, if I want to take an output, then I have to make that provision here, all right. So, next step is to essentially replace one of these mirrors by a partially transmissive mirror. Okay. So, instead of this condition, I can have now R1 equals to 100% and R2, say I make it 98% say. So, 2% of light will pass through this mirror. So, every time it bounces off this mirror, 2% of that light will go out. That is what it means. So, this is completely reflective and this one is partially transmissive. Okay. So, once I have that, I can have an output, all right. So, this is more or less what how you will construct a laser. So, this is my laser. So, I have found out a way to fill this blank by putting the active medium in a resonator. Okay. And we also got the output by instead of putting 100% reflective mirror on both the ends, make one of them partially transmissive. So, we get an output. Now, there are this is a very basic concept. There are so many things there, right, which one needs to consider, and we will learn some of them. Say I will give you one example. I have been saying that 100% reflective mirrors, okay, but actually getting 100% reflectivity is very, very tough. Second, I said I will be using a flat mirror, all right. So, this flatness of the surface, okay, that also may not be as you expected. It can be a little rough even at a very, very small dimension, but getting absolutely flat surface is a big deal. So, that will give rise to some loss of photons, right. I assumed that okay, all the photons are going and hitting and coming back, going and hitting and coming back, but if suppose the mirror is not flat, so what will happen? It will deflect. The moment it deflects from this axial direction, it will escape the cavity, right. So, roughness of the surface or a little bit faulty mirror. When I say faulty, that means it has a reflectivity which is less than 100% for one of the end mirrors, not the one that is purposefully or intentionally made transmissive. The other one which is supposed to be 100% reflective, if it does not have 100% reflectivity, then we are going to lose photons. Okay. So, this is generally called loss. Okay. So, there are several different types of reasons that will give rise to loss of photon, and these are some we will talk about certain losses. Now, if we have to really get laser output which is like really amplified signal, one has to amplify it so much that is capable of overcoming the losses and we get a net output. So, what we have to have? We have to create a gain over the losses, right. So, there will be certain conditions which will be called threshold conditions. We will talk about that maybe the following class. So, we will know how quantitatively we can figure out how we can reach the threshold condition and then beyond and go and get laser output. Okay. So, we have seen that this resonator cavity can give us it's extremely helpful, and actually this is very crucial in order to get the laser output. Fine. So, we will come back to this discussion of these practical issues involving the construction of laser. Okay. In the meantime, let us look at certain other things which will be essential in order to move forward. So, for example, we will now talk about certain concepts like modes of laser and standing wave. So, we will talk about standing waves, and modes. We will see how it is relevant to this case. Okay. So, as we said just a few minutes back, that by design my stimulated emissions or stimulated photons have all the characteristics same as that of the spontaneous photon, and one of these criteria is the phase, correct. So, identical phase for all the photons, and because of which we called the output ultimately as coherent, right. So, this concept of coherence comes from this having identical phase as that of the spontaneous photons, which triggers the stimulated emission in our laser construct. Now, if we talk about the quantum theory of light. So, in quantum theory of light, it is very common, it is very usual to refer to the modes of light, okay, or modes of photon modes of photons, modes of light to characterize the photon. So, normally we say okay, this beam is coherent, so it refers to that, okay, it has the same phase. Now, in quantum theory of light, when we say that okay, this is the mode of the photon or this is the mode of the light, this actually tells you some characteristics of the light, right. So, light characteristics. Now, what is meant by these modes of photons? Okay, this is extremely relevant to our context. So, modes essentially it represent the possible combinations of frequency, polarization, direction of the light. Okay. So, what kind of combination that I have will dictate what mode I have. Okay. Now, whether all the modes that are possible in principle can actually be sustained in a laser cavity That is a question. So, what we will do in the next class is to find out whether you know, all the modes that are possible in principle can be there in this cavity. If yes, how? If not, why not? And then what are the modes that we can actually generate. All right. So, we will meet again in the following class. Till then, have a good day and or good night, whatever it is, and thank you very much for your attention.